Welcome to this lecture series in linear algebra. In this lecture, we'll look at some applications of the rank nullity theorem and let us recall the relevant things. So we need to know about polynomials. Again, so far we haven't seen a very formal treatment of polynomials, but what we have done is sufficient. And you can, if you are really uncomfortable with polynomials, then you can skip the discussion on polynomials that we will undertake and come back to it later. Alright, we need to know only one fact about polynomials, that a polynomial of degree n cannot have more than n distinct roots. We haven't really defined what roots are, but I'm sure you're familiar with them, at least in the context of polynomials over real numbers. Okay, and we of course need to know about the rank nullity theorem, which says what? Which says that if we have a linear map, again all the vector spaces are finite dimensional, then the dimension of the kernel of T plus dimension of the image of T is equal to dimension of the domain. Okay. Here are some problems for practice. And now let us get started. So suppose, our first application is about endomorphisms. So suppose we have an endomorphism on a finite dimensional vector space V, then it is injective if and only if it is surjective. And this is very interesting because in general an injective function may not be surjective, but in the context of linear algebra it turns out that injective functions are same as surjective functions, where of course we are assuming it's a self map. It's a linear map from V to itself, and this is the statement. So let's prove one direction. There are two directions to prove, but if we give the proof of one of them, the proof of the other direction will be automatically obvious. So assume T is injective. Now by rank nullity theorem, we have this equation, but by injectivity this is 0. Injectivity of T implies the kernel of T is trivial, and hence this is 0, and therefore the dimension of the image is the entire. Right, this is the case, but since image T is contained in V, after all the target of T is V as well as the domain, this implies that image T must be equal to V. And you can just reverse this reasoning, or not really reverse, but suppose if you assume that T were surjective, then this would be the entire, this would be equal to the dimension of V, and this would cancel out, and therefore the dimension of the kernel would be 0, which means that the kernel is trivial. Okay, so that's it. There's a very simple proof of a very interesting result. A corollary is the following. Suppose we have two linear endomorphisms on a vector space V. Again, everything is finite dimensional. And suppose it so happens that S composed with T is identity, and as a point of notation, let me mention that when we write S composed T, we just write ST most of the time. So suppose S composed with T is identity, then T composed with S is identity, and vice versa. Again, this is quite different from what happens in just purely set theoretic contexts. In linear algebra, these things happen. All right. So how do we do this? Suppose, assume this is identity, and we want to show that that guy is identity. So first of all, note that since this is identity, T is injective and S is surjective. Right? This is a set theoretic statement. If this happens to be identity, nothing to do with linear algebra, it automatically forces that T is injective and S is surjective. But since T is a linear endomorphism, this implies T is also surjective and S is also injective. So both S and T are bijections, and therefore Now it's a set theoretic thing. Therefore, we have this equation that we started with implies T is the inverse of S, which implies this is the case. So from this point on, it's just a set theoretic deduction. Okay. Now we come to polynomials. So first of all, we will make a comment about polynomials as functions. As of now, we think of a polynomial. Suppose we have a field f and a polynomial of degree at most n over the field f. So recall this notation is for all the polynomials of degree at most n over the field f. So if we have px in that, then we just think of it as a formal sum of the sort where each alpha I is a member of f. But given such a polynomial, we can define a function, evaluation function coming from P, which consumes an element of the field and outputs an element of the field. How is it defined? It takes an element beta and outputs this particular element of the field. So what's going on? All we have done is just substitute beta in place of x. Here x was just a placeholder. It did not have any meaning, so to say. But here we are getting a function. It consumes an element of the field and produces this element of the field. This is a meaningful element of the field because each alpha I and beta are elements of the field. So this is a field element, that is a field element, and so on. And therefore their sum is also a field element. So this is the function coming out of this polynomial. And in high school, we do not differentiate between these two things. In fact, in high school, we always think of polynomials as functions. Over the real number field, the difference is only superficial, but in a general field, the difference can be significant. So we should keep in mind that polynomials are not functions per se, but they can give rise to functions. At the same time, let me mention about this notation. This thing on the right hand side is written as p beta. So the evaluation of p at beta is written as just p of beta. Familiar from high school. Okay. All right. Now, what about what is meant by polynomial interpolation? So, just to motivate it, suppose we are working with real numbers. This is the real number line. And we are given two numbers, x1 and x2. And we are also given values corresponding to them. So there is some data set which consists of only 2 points, where you have distinct inputs, x1 and x2, and these are the outputs that you get. The outputs may not be distinct, but in this picture they look distinct. Now the question is, can you fit a curve according to this data, which confirms to this data? Of course, you can fit many curves. Sorry about that. You can fit many curves, but what one would like to do is to be cost effective. So what we want is, or it is natural to demand, a polynomial that fits this and of smallest possible degree. So here there are only 2 points, and it's easy to see that one can fit a straight line, which is a degree 1 polynomial. In fact, it could also be constant if y1 were equal to y2, in which case it would be a degree 0 polynomial. So you can do with degree at most 1 when you have only 2 points to fit. Maybe it's a good idea to draw. So this is a polynomial that fits the data. What about the other situation? Here we have 3 points, 3 inputs, distinct, and 3 outputs, not necessarily distinct, even though in the picture they look distinct. Again, we would like to find a polynomial that fits this data, and in general, one cannot necessarily do with just a degree 1 polynomial, because these 3 points may not be on a line. But if you think about it, or give it some thought or something, it's the same thing. What you would find is that you can manage with a degree at most 2 polynomial. This is not completely obvious, but if you think about it, you will surely get it. So here, let me try to fit it. Hopefully, I'll be successful. pretty much there. I don't want to spend more time on it. So you can find a degree 2 polynomial which fits it. And this is what we are going to prove, that no matter what what number of inputs are given and corresponding outputs are given, you can always find an appropriate polynomial of reasonable cost. In fact, the best cost, I would say, that fits the data. So here is a formal statement. Fix any field. For comfort, you can take it to be real numbers. And suppose we have n distinct elements of the field. Then for any n values in the field, not necessarily distinct, there is a polynomial of degree at most n minus 1. So when n were 2, we saw that a degree 1 polynomial sufficed. And when n were 3, a degree 2 polynomial sufficed. In general, for n inputs, a degree at most n minus 1 polynomial will suffice to fit the data. Px1 is y1, pxn is yn, and in between pxi is yi. So, and you cannot do better than this in general, that I leave you to think about. But you can definitely do with this much, and that is what we are going to do. The proof is actually very simple, but it's an enlightening proof. Okay. So we have this vector space, all right, and we define a map from this to that thing. Note that both vector spaces have the same dimension. Don't get fooled by this n minus 1. This is a vector space of dimension n, and so is this. And what is the definition? T takes a polynomial px and outputs the evaluations at various xi's. Perhaps it was better to call them alpha i's, but now I don't want to change anything. So this is the definition of T. Okay. So again, just to remind, this is the evaluation of P at the point x1. x1 is not a variable or anything. So this is our map, and the point is to check that this is linear. Very easy to check. This is a linear map, and we want to show that it is surjective. This is really what the theorem asks us to prove. Why? Because what it is saying is that for any y1 up to yn, there is some polynomial that fits the data. Meaning, once you choose y1 up to yn, there is some polynomial for which t of px is same as this thing. That's exactly what this means. So once you realize that, we want to show that t is surjective. But since these two vector spaces are of the same dimension, we just need to show that t is injective. So suffice us to show that. Well, we didn't really prove this particular statement, but we did a simpler version of it. So let me outline what I'm really using. I'm using this fact that if t v to w is linear and dimension v is equal to dimension w, then t is injective if and only if t is surjective. We are using this fact. What we proved is when w were equal to v. That is the application that we saw. But we are using this, but at the same time, if you look at the proof of what we gave when w were equal to v, we only used the fact that these two spaces have the same dimension. Not that these two spaces were the same, just that they had the same dimension. So just apply rank nullity and you'll get it. I'll formally make this an exercise in the next lecture or so. Okay, so suffices to show that t is injective. How do we show t is injective? We just record the kernel. So let's say p is in the kernel. Then this is the 0 of the target, which implies that, but this means that you have a polynomial of degree at most n with at least n distinct roots. Each xi is a root of that polynomial, and the only polynomial with that property is the 0 polynomial. This is a fact that we will formally prove later in the course at some point, but I'm sure this is familiar from high school. At least we hear this in high school, even though we may not properly prove it. But or you can Google around. So a polynomial of degree at most n can of at most n minus 1 can have at most n minus 1 distinct roots. But here we are seeing n distinct roots. So that can only happen when the polynomial is 0, constant polynomial 0. Therefore, P is the 0 polynomial. Px is 0, and hence kernel T is trivial, which implies T is injective, which finishes the proof. It's a very nice application of linear algebra to something that is outside of linear algebra. This fact in and of itself has nothing to do with linear algebra, but we have used linear algebra to prove it. Okay, I think this is all for this lecture. As usual, like, comment, share, subscribe, and I will see you next time.